नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT JEE एंड नीट। वीडियो शुरू करने से पहले आप लोगों से अनुरोध है कि यदि आपने हमारा चैनल सब्सक्राइब नहीं किया है तो प्लीज इसको सब्सक्राइब करें। ये वीडियो जेईई मेंस को ध्यान में रख के बनाए जा रहे हैं। ये उन बच्चों के लिए भी इम्पोर्टेंट है जो अपनी बोर्ड की तैयारी अच्छी तरह से करना चाहते हैं। तो आइए वीडियो शुरू करते हैं। सॉलिड स्टेट पार्ट 2 वीडियो देखने के बाद यदि आपको ये अच्छा लगता है तो प्लीज इसको सब्सक्राइब जरूर करें। सॉलिड स्टेट पार्ट में 1 में हमने क्यूबिक क्रिस्टल्स को मेनली डिस्कस किया था और ये डिस्कशन पूरा जेई पास्ट ईयर क्वेश्चंस को देख के किया जा रहा है। सो नाउ टुडे वी आर गोइंग टू डिस्कस अबाउट आयनिक क्रिस्टल्स, देन आफ्टर दैट वी विल गोइंग टू डिस्कस अबाउट द डिफेक्ट्स इन सॉलिड्स एंड देयर एप्लीकेशन इन देयर इलेक्ट्रिकल एंड मैग्नेटिक प्रॉपर्टीज। चलिए शुरू करते हैं। Okay, so here we are starting with HCP metallic crystal. So regarding HCP metallic crystal, very few questions they have asked in JEE mains. So keeping that in mind, we are discussing this HCP metallic crystal. So the first thing is, if you discuss about HCP metallic crystal, there are two type of unit cell. One is known as hexagonal close pack prismatic unit cell and the other is parallelopipe. So in general, when we are discussing about three-dimensional unit cell, all the three-dimensional unit cell are parallelopipe, but especially in HCP, we are discussing prismatic unit cell. So this is prismatic unit cell. In this prismatic unit cell, you can see here that the atom present at the hexagonal face, the atoms present at a corner has a contribution of 1/6, at face center has a contribution of half. The same thing is repeated at the bottom, and in middle there is a plane where there are three atoms which is just inside this hexagonal unit cell. The center of these atoms lies inside the hexagonal unit cell, but these are not completely inside the hexagonal unit cell. This thing is mentioned in your NCERT. That's why I'm saying that these three atoms in the middle is not completely inside, but their center is inside. So its contribution is equal to 1. So when we calculate that, what is the number of atoms in HCP prismatic unit cell? So there are 12 corners of regular hexagon, 6 top and 6 bottom. Their contribution is 1/6 because this angle is 120 degree. So we can place 3 unit cell along with this one, total 3. Along with this we'll place 2 and 3 above. So this corner is shared between 6 unit cell, so its contribution is 1/6. We can place one more unit cell above this, so its contribution is half. So 12 into 1/6 plus 2 into half plus those which are inside, they are fully inside this, their center is fully inside this, so their contribution is 1, though they are not complete inside the hexagonal prismatic unit cell. So total number of atoms per unit cell is equal to 6. Nearest metal atoms in any metallic crystal, nearest metal atoms will touch each other. So the nearest distance between, we are discussing about hexagonal unit cell. So the dimensions are A is equal to B is not equal to C, alpha is equal to beta is equal to 90 degree and gamma is equal to 120 degree. So here A and B are same, but C is different. So the nearest atoms is along this A edge length. So A is equal to 2R, they are touching each other. So A is equal to 2R. Relation between C and A, when we'll discuss for JEE Advanced, we are going to derive this relation, but I don't think that there is need here. So I'm using directly that this height is equal to under root 8/3 times of edge length. So C is equal to under root 8/3 times of edge length. Volume of unit cell we can calculate because at the bottom there are 6 equilateral triangle in this regular hexagon. Area of one equilateral triangle is under root 3/4 square multiplied by 6. So from there we have calculated what is the area of the base. Once we know the area of base, we'll multiply by height, we'll get the volume of this hexagonal prismatic unit cell. So density of, so if you calculate the volume in terms of radius of atom, that is equal to 24 root 2 r cube. Density of unit cell is equal to mass of unit cell. There are 6 atoms. Mass of one atom is atomic mass divided by Avogadro number. Be careful about the unit. Generally, if the density in gram per meter centimeter cube, then this atomic mass is in gram. But if it is in kg per meter cube, this atomic mass should be divided by 1000. And this is the volume. So if we place, we'll get the density of hexagonal close pack metallic crystal. Packing fraction, again volume occupied by atoms upon volume of unit cell. Volume is 6 into 4 by 3 pi r cube. This is the volume occupied by atoms, and volume of unit cell is 24 root 2 r cube. So from here we can find out that packing fraction is pi by 3 root 2, which comes to be 0.74. So the packing fraction of metallic hexagonal close packed crystal and FCC metallic crystal is same, that is equal to 0.74. Now most of the questions they are asking about HCP metallic crystal is, they will say that if this is the mass of the crystal, the density of the crystal is given, you can find out what is the volume, and from there you can find what is the mass of unit cell. So mass of the crystal upon mass of unit cell will get number of unit cell. From there we can find out how many atoms are there. So these type of questions are there. Or mostly they are saying that if this is the number of atoms, how many tetrahedral voids are there, or how many octahedral voids are there. For any close packed crystals, the number of tetrahedral void is 2 times the number of atoms, and the number of octahedral void is equal to the number of atoms. And since these are close packed, they have octahedral void and tetrahedral void. So we know that what is the relation between radius of octahedral void with respect to radius of atom. So the derivation is same for metallic crystal, either it is FCC or HCP will make an regular octahedron, and from there we will derive. So already this has been done for FCC. So we are writing that radius of octahedral void is 0.414 times radius of atom, and radius of tetrahedral void is 0.225 times radius of atom. Radius of octahedral void is greater than radius of tetrahedral void. And coordination number we can find out in FCC as well as SCP. Coordination number is 12, because we can see here that the atom present at the top face is touching these 6 atoms in the same plane. Then they are touching these 3 atoms below at the center of this prism, and there is an other prism above it. So there are 3 atoms at the center of that. So this atom is touching these 6 atoms in its plane, 3 below and 3 above. So its coordination number is 12. Now we are going to discuss about ionic crystals, and in ionic crystals, basically when I was going through the past year questions, they have asked very simple type of question based on that. So keeping that in mind, I am doing the discussion. So in ionic crystal, in case of binary ionic solids, binary means it is made up of 2 elements, one cation, one anion. So it is binary, one type of cation and one type of anion. So in any ionic crystals, binary crystals, when we are discussing, nearest cation and nearest anion will always touch each other. Usually anion is larger in size than cation, not always, but usually anion is larger and cation is smaller. Larger ion is present on lattice sides. If I am saying that crystal is FCC with respect to anion, means anions are present at corners and face center, and there is tetrahedral and octahedral void. So these are small sides. So on small sides, small ions are present, and generally cations are small ions. So cations are present, smaller ions are present in void. As the radius ratio will increase, radius ratio is radius of cation upon radius of anion, or radius of small ion upon radius of big ion. So radius ratio will increase, then coordination number will increase. Like when we are discussing about tetrahedral void, if a cation is present in tetrahedral void, the radius of cation upon radius of atom is 0.225. When we are discussing about octahedral void, radius of cation upon radius of anion is 0.414. When we are discussing about cubic void, where coordination number is 8, radius of cubic void upon radius of anion is 0.732. So as the radius ratio is going to increase in ionic crystal, the coordination number is going to increase. There is a difference in ionic and metallic crystal. The maximum coordination number in metallic crystal is 12, while the maximum coordination number in ionic crystal is 8. Ratio of number of ions, this is a very important point. 5th point, ratio of number of ions is inverse of their coordination number. So we are going to discuss an example, though this example is not very useful for us regarding math. Suppose if I am writing A2B, A2B means Na2O type of crystal. So this Na2O type of crystal, this oxide ion, it is FCC with respect to oxide ion, and this Na plus ion is present in tetrahedral void. Since this Na plus ion is present in tetrahedral void is a vacant space which is equidistant from 4 atoms or ions. So something in tetrahedral void means coordination number of that is equal to 4. So coordination coordination number of cation is 4. But from this formula you can see that this oxygen atom is surrounded by more number of cations. So the ratio of atom is 2:1, but the coordination number of this cation is 4. Then the coordination number of this anion should be 8. Coordination number of anion should be greater than coordination number of cation, because anion are surrounded by more cations, 2:1 ratio. So this is always valid for binary solid. Ratio of number of ions is inverse of their coordination number. So we are going to use this in binary ionic solid. So let us take an example, and this is an example where we are discussing about cesium chloride. This is CaCl type of crystal, CaCl type of ionic crystal. So in this CaCl type of ionic crystal, the first point you have to remember, like in simple cubic metallic crystal also, you have remembered that atoms are present at the corner. In BCC, you have remembered that atoms are present at corners and body centers. Same way, when we are discussing about CaCl type of crystal, first line you have to remember, this line is important, that it is simple cubic with respect to anion, and cation is present in cubic void. So here is the structure of this CaCl type of crystal. Now, if you know this point, with the help of this point, we can derive many points logically. So if you remember the first point, now from here, if it is simple cubic, I can write that number of anions per unit cell is equal to 1. From the formula, it is AB type of crystal, the number of cations and anion is equal. So from there we can say that the number of anion is 1, then number of cation per unit cell is equal to 1. So number of cation and number of anion per unit cell is equal to 1. Now number of formula unit per unit cell. Formula unit means one formula unit of CaCl contains one cation and one anion. In one unit cell there is one cation, one anion. So we can say that number of formula unit per unit cell is equal to 1. So if we know the first point, logically we can find out what is the second, third point from this first point. From here we can find out all these 3 points. Now coordination number, since we remember the first line that it is simple cubic with respect to anion and cation is present in cubic void. If cation is present in cubic void is a vacant space which is equidistant from 8 ions. So these ions are at the corners and this body center is cubic void. So we know that if someone is there in cubic void, coordination number is 8. The ratio of atoms is 1:1. Inverse of this is also 1:1. So coordination number of cation and anion is equal. So that is equal to 8. Coordination number of cation and coordination number of anion. For one ion, you have to remember the first line. And with the help of formula, we can find out the coordination number of the second ion. Now here we are discussing always valid condition. In an ionic crystal, nearest cation and nearest anion will always touch each other. So from the center of this cation and center of the anion present of any one of the corner, this distance is half of the body diagonal. So we can write that radius of cation plus radius of anion is equal to √3 a/2. Limiting condition, this is not always valid. This is valid when the packing fraction is maximum, because anion will repel each other. So if the anion is touching each other, it is not very stable situation, but maximum what can happen, that the nearest anion will touch each other. When the anion will come nearer to each other, the space between them is going to decrease, so packing fraction is going to increase. So this is known as limiting condition. In limiting condition, the nearest anion will touch each other. So 2 times radius of anion is equal to edge length, or radius of anion is equal to edge length divided by 2. So from this equation number 1 and equation number 2, if I divide equation number 1 by equation number 2, on the left hand side I can write that radius of cation plus radius of anion upon radius of anion is equal to √3, and that will give you radius of cation upon radius of anion is equal to 0.732, that is √3 minus 1. So this is also the relation we are using, that if it is present in cubic void, the radius of cation or radius of cubic void is equal to 0.732 times the radius of anion. And this is the limiting condition, because in cubic crystal, when we are discussing ionic crystal, the radius ratio lies between this range. Radius of cation upon radius of anion should be greater than equal to 0.732 and it should be less than 1. So this is the limiting condition when the nearest anion are touching each other. So under that condition, when the space between anions will be less, packing fraction will be maximum. So if we want to calculate the packing fraction, that is volume occupied by ions upon volume of unit cell. So volume occupied, since in this crystal there is one cation, one anion, volume is 4 by 3 pi r, radius of cation whole cube 4 by 3 pi, radius of anion whole cube upon volume of the unit cell. And from this we can derive the relation between radius of cation and edge length and radius of anion and edge length, and by using that relation we can calculate the packing fraction. Why I'm discussing till now regarding packing fraction, they have asked a question in JEE mains where they have placed that the ion present at the center is 2 times in radius with respect to some other crystal where the radius is different, and then they are comparing that what fraction of volume is occupied or what is the packing fraction. So these type of questions has been already asked in JEE mains, so that's why I'm discussing it. So method is important. You will do the calculation. NaCl type of crystal. The first line of any binary ionic solid is important. So when I'm discussing about NaCl type of crystal, it is FCC with respect to anion and cation is present in octahedral void. You have to remember this line. If you remember this line, all lines can be derived from that. So the second is the number of cation per unit cell. Since it is FCC with respect to anion, we can say that number of anions per unit cell is 4. And the formula is NaCl AB type. Ratio of cation and anion is equal. From there, we can say that number of cations per unit cell is equal to 4. In one formula unit, there is one cation and one anion. So per unit cell, there are 4 cation and 4 anion. So we can say that per unit cell, there are 4 formula unit in NaCl type of crystal. Coordination number from the first line, if we remember that cation is present in octahedral void, then we can say that coordination number of cation is equal to 6, and the ratio of atom is 1:1. Inverse of that is 1:1, means the coordination number of anion is also equals to 6. So this is the structure of NaCl where anions are present at the corners and face center. So corners and face center. So and the cations are present in all the octahedral voids. All the octahedral voids are occupied. So this is an octahedral void, edge center, and this is body center. So all 12 edge center and body center is occupied. So 100% of the octahedral voids are occupied in NaCl crystal. Now fourth point, this is important, always valid condition. Nearest anion and nearest cation will always touch each other. Since it is cation is present in octahedral void, we can say that the distance, nearest distance between cation and anion is edge length divided by 2. So radius of cation plus radius of anion is equal to edge length divided by 2. And this is limiting condition. This condition is not always valid. It is valid when anion will touch each other. When anion will touch each other, the packing fraction will be maximum because the space between the anions is going to decrease. So here if it is FCC, the nearest distance between, it is FCC with respect to anion, nearest distance between two anions is equal to face diagonal half. So 2 times of radius of anion is equal to a by root 2. From there we can find out that edge length is equal to 2 root 2 times radius of anion. So this is equation number 2. Radius of anion is a upon 2 root 2. By dividing equation 1 by equation 2, we can say that radius of cation upon radius of anion plus 1 is equal to root 2, or radius of cation upon radius of anion is equal to 0.414. So radius of cation, or we can say this is radius of tetrahedral void, sorry, octahedral void. Radius of octahedral void is equal to 0.414 times radius of anion, and radius of anion is edge length divided by 2 root 2. So this is the relation between radius of cation and edge length and radius of anion and edge length. And same way, if they are asking what is the packing fraction is equal to volume occupied by ions. There are 4 cations and 4 anions. So volume occupied by them is 4 into 4 by 3 pi r radius of anion whole cube plus 4 into 4 by 3 pi r radius of cation whole cube divided by volume of the unit cell. Volume of the unit cell we can write as edge length cube, and using the relation between radius of anion upon edge length and radius of cation upon edge length, we can write the packing fraction. So this is about NaCl crystal. Now we are going to discuss only these type of questions are there, so I'm not going to discuss about other type of ionic crystal. This is enough according to JEE main. So now we are going to discuss a very important point, defects in crystal. This is very important with respect to JEE mains as well as with respect to JEE advanced, because there are so many applications of properties of solid we are using in our daily life. When we are using our mobile, we are saving messages, we are deleting messages, we are using the magnetic properties of the solid. So many applications nowadays are there. So defects in solid is the most important topic. You should not leave it. If you go through the papers of mains and advanced, so many questions been asked about this topic. So starting from defect in solid, there are many type of defect like point defect, line defect, and volume defect. But line and volume defect is not in our syllabus. We are discussing about point defect. This point defect is also known as thermodynamic defect. It means it is related to temperature. Because of changes in temperature, the ion is not present in its position, it is missing from the crystal, or it is dislocated from one position to another position. That's why this defect is known as point defect. So this point defect can be divided into two categories. The first one is stoichiometric defect. When we discuss about stoichiometric defect, the formula of defected crystal and the formula of perfect crystal is same. So in a stoichiometric defect, the formula is not going to change, while in non-stoichiometric defect, the formula of defected crystal is different from the formula of perfect crystal. The ratio of atoms or ions in the crystal when it is perfect and when it is defected is different. Stoichiometric defect, it can be divided in two type of crystal, metallic or atomic crystal and ionic crystal. In metallic crystal, there is two type of defect, vacancy defect and interstitial defect. In case of ionic crystal, there are two types of defect, Schottky defect and Frankel defect. And non-stoichiometric defect is of three types. We are going to discuss one by one. This can be divided into two parts, metal excess defect and metal deficiency defect. So we are going to study about these. So the first thing is about defect in metallic or atomic crystal, that is vacancy and interstitial defect. So if it is a perfect crystal, this atom should be present here, but now it is missing from this position, so it is a vacancy defect. If it is missing, if atom is missing, there is a decrease in mass of the system, volume remains same. So due to vacancy defect, the density of the crystal will decrease. This is the question they are going to ask, that vacancy defects say what is the effect on density. In interstitial defect, atoms are present at their sides as well as interstitial sides. Interstitial sites means it is the place between the atoms. This place is known as interstitial site. So an extra metal atom is here in interstitial site, and because of that, the density of this crystal is going to increase. So this defect, vacancy and interstitial defect, is found in metallic or atomic crystal. Because of vacancy, density will decrease. Because of interstitial, density is going to increase. Now Schottky and Frankel defect is observed in ionic solid. So in case of Schottky defect, equal number of cation and anion is missing from their lattice side. That is mentioned in NCERT. But when we discuss logically, like if the crystal is such that the cation and anion are missing from the crystal in their stoichiometric ratio, then that should be the Schottky defect. Since most of the Schottky defect is observed in those crystals having from formula AB type. That's why in NCERT they have mentioned that if equal number of cations and equal number of anions are missing from the lattice side, then that defect is known as Schottky defect. So this is the first point. The second point is, due to this defect, because mass is missing from the crystal, so the density of the crystal is going to decrease. This defect is observed in the crystals having high coordination number. It's very logical because the cation is usually small and anion is big. So cation and anion are both missing from this crystal. They have to move through the crystal. They are missing from the crystal. It means that anion and cation can move easily in the crystal. That is possible when the difference in the size of cation and anion is small. And that is possible when the coordination number is high. That's why they are saying that this defect is observed in crystals having high coordination number. And these examples are given in NCERT. So in high coordination number, like in CSCl, we have to study about three type of coordination number in ionic crystal: 4, 6 and 8. 8 is high, 4 is low, and 6 is intermediate between them. So in some cases we'll consider 6 in high coordination number, in some cases we'll consider it in low coordination number, because for coordination number 6 also there is a range of radius ratio, that is 0.4142 to 0.732. So that's why for 6 we have, sometimes we consider it on the left hand side, sometimes we consider it on the right hand side. So CSCl has coordination number 8, so it has Schottky defect. NaCl has coordination number 6, Schottky defect. KCl is same type of NaCl. AgBr having Schottky defect. This AgBr is important because it can show Frankel defect as well as Schottky defect. It has both. It can show both type of defect. Now one numerical which they are going to ask is very logical. Suppose this all sites are occupied, all sites of cation and anion is occupied. So whatever the density is that we can say theoretical density, or we can say density in a perfect crystal. So density in a perfect crystal or theoretical density is corresponding to 100% of the sites are occupied. Now if I'm using unitary method, that if the density is unit, how many percentage sites are occupied? So 100 divided by theoretical density. And now this crystal has defect, and from experiment we have find out what is the density of this defected crystal. So density of this experimental value of density is regarding defected crystal. So we want to know that what percentage of sites are unoccupied or occupied in this crystal. So percentage sites occupied, we are using unitary method, that for 100% density should be density theoretical. If density is 1, what is the percentage sites occupied? Now in this crystal the density is this, so what is the percentage sites occupied? That is equal to d experimental upon d theoretical into 100. So from here we can calculate that what is the percentage site unoccupied, that is 100 minus percentage sites occupied, 100 minus d experimental upon d theoretical into 100. So if you simplify this, we are getting that percentage of Schottky defect, Schottky means unoccupied site, that is equal to d theoretical minus d experimental upon d theoretical into 100. So this is a fixed question based on Schottky defect, important for mains, board exam also, as well as advanced. Frankel defect. So when we are discussing about Frankel defect, the first point is it is also known as dislocation defect. Why it is known as dislocation defect? According to this, the small ion here, sphere is cation and big one is anion, cation, anion, these are there. Now this cation is missing from its lattice site and it is present in interstitial site. So it is dislocated from its position. So there is no change in mass, there is no change in volume. So fixed question is there that because of Frankel defect, there is no change in the density of the crystal. So it is also known as dislocation defect because cation is moving from its site and occupying some interstitial position. There is no change in density of the crystal because mass and volume both are same. This defect is observed in those crystals having low coordination number. Why? Because cation is small in size and it is moving, anion is not moving. So if this is moving, means the difference between the size of cation and anion is large. So this is observed in those crystals having high difference in size of cation and anion, means coordination number will be low. So that is the third point. Now this is important. They will ask that these type of crystals, which type of defect they will show. So zinc sulfide, when we study about zinc sulfide, it has two type of structure, woodsite and zinc blende. But today we are not going to study. Zinc sulfide has diamond type of a structure, right? Atoms are present at corners, face, center, and alternate tetrahedral void. But we are not going to discuss that. So zinc sulfide coordination number of cation and anion both is 4. So low coordination number. Similarly, AgCl, AgBr, and AgI. And the most important point is AgBr. So there is a fixed question that AgBr can show. It can show both type of defect, Frankel defect as well as Schottky defect. And this point is also asked in JEE Advanced. Let us logically discuss this point. The crystals having this defect has high value of dielectric constant. So let me explain. When we are talking about zinc sulfide and we are saying that the difference in the size of Zn2 plus ion and the size of sulfide ion is large. This cation is small and this anion is large. So because of large difference in size of cation and anion, there is polarizing power of this cation will be more and polarizability of this anion will be more, right? So because of that, this anion will distort and there is sharing of electrons, we can say, between this cation and anion. Because of this distortion, the ionic character of this solid is going to decrease. So when we are discussing about the force of attraction between this cation and anion, we can say 1 upon 4 pi epsilon naught, that is equal to K Q1 Q2 upon R square. As a result of this covalent character sharing of electron, because of that, this force of attraction is decreasing, and that can be explained by dielectric constant, because when we are writing this K, we are writing 1 upon 4 pi epsilon naught in vacuum, but in a medium, that is epsilon naught is related into, that is epsilon of permittivity of that medium, that is equal to permittivity of free space into dielectric constant. So if this dielectric constant is going to increase, this force is going to decrease. So there is another way to say, because of sharing of electrons, if there is covalent character in ionic solid, we can say force of attraction will decrease, and force of attraction will decrease, we can indirectly say that the dielectric constant of that medium is high. Okay, so if dielectric constant is high and charged particle is there, their force of attraction in that medium will be less, means the ionic character will be less. Now non-stoichiometric defect, this is most important, non-stoichiometric defect. So there are two type of non-stoichiometric defect. We know that the formula of the defected crystal is different from perfect crystal. So we are discussing first metal excess defect, then we are going to discuss about metal deficiency defect. So metal excess defect due to anion vacancy. So in this metal excess defect, what we are doing, we have taken a perfect crystal of NaCl. NaCl crystal is heated in presence of sodium vapor and allowed to cool. So we know that sodium is alkali metal and the ionization energy of alkali metal is very low. So if we are heating, those alkali metal in vapor state will ionize, they will convert into Na plus ions. So now with cooling, those Na plus ion will allowed to settle down on this solid. So what is happening here, that this is Na plus ion, this is Na plus ion, this is formation of new. Till here old crystal was there. Now due to cooling, this Na plus ion will settle down here. So these are the new Na plus ions. In order to support these ions, Cl minus ion from this crystal is moving and coming at this position in order to develop the new crystal. So anion is coming from their side and occupying this side. So that's why the name is, because extra metal ions are coming, right? So metal excess defect due to anion vacancy, right? So because extra metal ion is coming, and because of that, these anions are leaving from their lattice sites and coming to support that, and the electron released by the sodium vapors when they ionized will occupy the position of these anions. So these are known as F centers. So what will happen, these electrons are in crystals, so they have force of attraction. When light will incident, photon will incident, they will absorb energy and they will go to higher state. And whenever any substance is excited, it is natural that it will de-excite. When it will de-excite, it will emit energy. When it is in visible color, that energy is in visible color, we can see the color. So NaCl should be colorless, because Na plus and Cl minus, Na plus all electrons are paired and it is alkali metal, Cl minus all electrons are paired. Due to DD transition, there is color, right? So because it is transition metal it is S block metal compound. In transition metal compound, generally transition metal compounds are colored. So this should be colorless, but their fixed question is there. Because of this defect, sodium chloride is yellow in color. Same type of crystal is LiCl and KCl. So these three colors are there, and fixed question is there, can you explain the color of these solids? Because these are expected to be colorless. NaCl perfect should be colorless, KCl perfect should be colorless, LiCl should be colorless. So in order to remember these colors, yellow, violet and pink, I have remember it like that. KCl has potassium chloride, its name started with P. So P के साथ P नहीं आएगा. Pink is not with potassium chloride. In this way, sodium chloride we always remember, okay, it is yellow in color. Between these two there is confusion. So we can make a logic that pink and potassium, they will not together, right? So the explanation of these S block ionic solids are colored is because of this defect, metal excess defect. And they can ask that because these are unpaired electrons, one electron there, this substance is initially diamagnetic in nature. It is diamagnetic because all the electrons are paired, and now one electron is there and they are unpaired. So because NaCl is diamagnetic, because of this defect it will become paramagnetic. So perfect NaCl is diamagnetic, defected NaCl is paramagnetic because of this defect. The second type of defect is metal excess defect due to extra metal ion in interstitial site, and the example is zinc oxide. Zinc oxide cold is colorless. On heating it becomes yellow color. We have to explain why the color is there. So this is a structure, perfect structure of zinc oxide. Small ion is Zn2 plus, big one is oxide ion. So what is happening that when we are heating this crystal, if we heat this crystal, what will happen that on heating the crystal, the anion oxide ion will participate in this redox reaction. Oxide ion is converted into oxygen gas by leaving these electrons. These electrons will remain in the crystal because in any crystal, ionic crystal, whatever, either it is perfect or defect, the charge must be balanced. Positive charge must be equal to negative charge. So here, this oxide ion is going, but the electrons are remaining, right? And these electrons are present in interstitial position. Again, these are like F centers in NaCl, defected NaCl. These are F centers because photon will incident, they will excite, then they will de-excite, and they will show yellow color, visible range, right? So again, the color is because of this defect and this F centers. Now, when we are heating, this oxide ion will leave its position in the form of oxygen gas, leaving these electrons in the crystal. And when we are heating and this anion is going outside the crystal, the nearby cation become unstable. So some nearby cation will leave its position and go to interstitial site. So it is leaving the position from the crystal and going to interstitial position. And this anion is missing from this lattice site. So anion is missing, but cation is present in interstitial position. That's why we are saying that this is extra, because if these are together, one is missing and this is going, so this is extra. So metal access defect due to extra metal ion in interstitial site. This defect is observed in crystals having low coordination number, because cation has to move in interstitial position. Smaller the cation, they can move easily. So radius ratio of cation and anion should be large. So this defect is observed in those crystals having low coordination number. And this is very important. This point is very important. Because of this defect, it has N type of semiconductor. How? If we place some potential difference, if we apply some battery, some electric or magnetic field, then this electron will move towards the positive electrode, right? This will move towards the positive electrode, and because of that there is conduction. So it is, when electron is moving like this, it is known as N type of semiconduction. And this is also important. On cooling, semiconduction will decrease. Why? Because when we cool, atmosphere contains oxygen, so those oxygen will take these electrons and they will convert into oxide ion. So this process will reverse. In this process, this electron is consumed, so semiconduction is going to decrease on cooling. Semiconduction is going to decrease on cooling. This third type of question is very common in board exam. JEE mains में इसको 2-3 बार पूछा गया, and this is also very important for JEE advanced. So the third is metal deficiency defect due to absence of metal ion from the lattice site. And this type of defect is observed in the crystals of transition element, because transition metal ions can show variable oxidation state. Like this defect is obtained in ferrous oxide. Iron is present in +2 as well as +3. Cuprous oxide, copper can present in +1 and +2. Nickel oxide, nickel can present in +2 and +3. And iron can present in +2 and +3. These all examples are given in NCERT, and most of the time we are discussing about FeO. There is a question in back of NCERT where they are discussing that which type of semiconduction will observe in defected Cu2O crystal. So these are very important. So now in this type of defect, we are discussing that this is a perfect crystal, but in defected crystal, what will happen? That some of the metal ion is missing from the lattice site. For example, in this, in FeO, perfect crystal, if Fe2+ ion is missing from its lattice site, either the crystal will be perfect or imperfect, charge must be balanced. So in order to balance the charge, because two positive ions are less now, so the nearby cation will convert into iron +3. So from +2 it is converted into +3. So because of that, now the charge is balanced. The magnitude of positive and negative charge is balanced. So in this crystal, some iron +2 ions are missing, and some of the iron +2 ions are converted into iron +3 ions. So there are two types of cation, divalent as well as trivalent. And there is a fixed question that what is the fraction of divalent cation, what is the fraction of trivalent cation. So the concept is balancing of charge. Charge must be balanced. So we can assume a crystal having 100 number of oxide ion. Suppose this is the formula of defective crystal Fe 0.960 perfect hota, so the formula should be Fe O hona chahiye tha. Now it is Fe 0.960. So if I assume that if I have taken a crystal in which 100 oxide ions are there, so magnitude of negative charge will be 200. So balancing the charge, we can assume that total iron ions, if this is 100, then this will be 96, because if it is 1, it is 0.96, so 100 is 96. So 96, assume iron plus 3 ion will be x, then iron plus 2 will be 96 minus x, balance the charge, 200, magnitude of negative charge is equal to 3 times the number of iron plus 3 ion, 2 times the number of iron plus 2 ion. If we simplify, we are getting x is equal to 8. So x is the number of iron plus 3 ions. So we can calculate that what fraction of iron plus 3 ions is what fraction of iron plus 3 ion in total iron ions. So that is equal to 8 divided by 96, or fraction of iron plus 2 ion in total iron ion. So that is equal to 88 divided by 96. So this is a fixed type of question. Apart from that, I am saying an important information about FeO. FeO is NaCl type of structure, rock salt type of structure. It has rock salt type of structure. So the first line of rock salt type of structure is anion is present in FCC and cation is present in octahedral void. So they can say that what percent of octahedral void is occupied, because NaCl, in NaCl all 100% octahedral void is occupied when the formula is FeO. But if now the formula is Fe 0.960, it means that only 96% of the octahedral void is occupied. Now they can say that what percent of octahedral void is occupied by iron plus 3. So again, same way, fraction you know, because 100% occupied means 96. Now iron plus 3 is 8. So 8 by 96 into 100. 100 by 12% is occupied by octahedral void is occupied by iron plus 3 and the remaining is occupied by iron plus 2 ion. So fixed type of questions regarding defected FeO crystal, and this is important because they are going to ask that which type of semiconduction it has. So it has N type of semiconduction, P type of semiconduction. Let me tell you that when we are discussing semiconduction in physics, silicon, when it is doped, then there is a semiconduction. So when we are discussing about P type of semiconduction, what happens that electron will jump from one bond to another bond, right? So when we are discussing about this silicon, and this silicon is doped with boron, right? So one of the surrounding atom is boron. So this is the structure. Now boron has only 3 electrons, so this is a vacant space. This is known as hole. This is electron. So what will happen that this electron from some other silicon atom will jump to this position, right? So this is known as Hooke's method. It is known as jumping of electron. Because of jumping of electron, there is conductivity. That is known as P type of semiconductor. So here also, if you see here, what will happen that this is iron plus 3. So what will happen that this iron plus 2 will give an electron to this iron plus 3, and electron will jump from here to here. So because of this jumping of electron, there is conductivity. So that conductivity is known as P type of semiconduction. So what will happen when this iron plus 2 will give electron to this itself is converted into iron plus 3, and this is converted into iron plus 2. So there is no change in number of iron plus 2 and iron plus 3, but in this process electron is jumping from one side to another side. This type of method of conduction is Hooke's method of conduction, or we can say P type of semiconduction. So this is P type of semiconductor. Extrinsic defect. Till now we are saying that all the defect is intrinsic. Intrinsic means we have not added any foreign particle, any impurity. But if we add impurity, then that defect is known as extrinsic defect. Or in case of semiconductor, when we are saying N type and P type semiconductor, they are extrinsic semiconductor, because in silicon if boron is added, it is impurity. In silicon if phosphorus is added, it is impurity. So when we are discussing about this extrinsic defect, suppose we have a fixed question. This is a question in NCERT, also asked in JEE mains. So let us go through the language of the question. If NaCl is doped with 10 to the power minus 3 mole %, this percentage, the defect is given in terms of percentage of SrCl2, then what is concentration of cation vacancies? So first we have to understand the meaning of concentration of cation vacancies. Concentration of cation vacancies means number of cation vacancies per mole of the crystal. You take 1 mole of the crystal and you count how many vacancies are there. So for example, we have taken for this example, suppose NaCl was in molten state. In molten state we have added molten SrCl2. So when we allowed the crystal this liquid to cool, the crystal will form. If it is perfect, then in NaCl this is the perfect crystal. Now because of addition of SrCl2, this defected crystal will form. So what will happen, that some of the positions of Na plus ion is taken by Sr plus 2. So this yellow color spheres are Sr plus 2. When Sr plus 2 will occupy, it has 2 positive charge. So one position is occupied. In order to balance the charge, you can see that 2 sodium atoms should be, Na plus ion should be missing with respect to 1 Sr plus 2. So one position of Na plus ion is taken by this Sr plus 2 and 1 is vacancy. So the number of Sr plus 2 ions is equal to the number of vacancy. So because of this defect, there is a vacancy, right? Again, since this vacancy is there, we can say that this Sr plus 2 ion can jump by Hooke's method from here to here, right? So again, it has a p type of semiconduction. It has a p type of semiconduction, and you should know what is the meaning concentration. So what we have to take? We have to take 1 mole of the crystal. In 1 mole of the crystal, we have to calculate what is the number of moles of SrCl2. So percentage is given. So we can say 1% ka 10 to the power minus 3%. You have to divide by 100. So this is 10 to the power minus 5 mole. We don't have to calculate moles. We have to calculate number of vacancies. So we have to calculate what is the number of formula unit of SrCl2. Number of formula unit of SrCl2 is number of moles of SrCl2 into Avogadro number. And we know that the number of Sr plus 2 ions is equal to this, and the number of Sr plus 2 ions is equal to the number of vacancy. So the number of vacancy, concentration of vacancy is 10 to the power minus 5 into Avogadro per mole of the crystal. So this is per mole of the crystal. So you should know what is the meaning of concentration of cation vacancy. Concentration of cation vacancies means number of cation vacancies per mole of the crystal. Now we are going to discuss about magnetic properties, and we know that substance is diamagnetic, paramagnetic, ferromagnetic. These properties of the crystals is experimentally determined, and from those experiments, with the help of theory, we are trying to find some logic, right? But the best way to find the substance is para or diamagnetic is doing experiment and find the property of that solid. So here when we are discussing about magnetic properties of the solid, all the magnetic properties of the solid is because of electrons. Origin of magnetic movement is because of electron, and electron is participating in 2 type of motion. One is orbital motion around the nucleus, and the other is a spin of the electron. Because of these 2 motions, there is magnetic movement in the electron, or electron can act like a tiny magnet, right? These are magnetic line of forces coming outside from North Pole and going inside to South Pole. So electron is behaving like a tiny magnet, and this magnetism is because of the motion of electrons, orbital motion and spin of electron. So every substance is made up of electron. It means that every substance should have magnetic property. Is it correct or not? So we know that if the substance has paired electron, then their spin, magnetic moment due to spin will cancel out each other, because we are saying that when they are in the same orbital, they will align in this way, right? So one of the electron is behaving like this type of magnet where north and south pole is like this, so the other one is behaving just opposite to it, and they will cancel out each other. So if the electrons are paired, magnetic moment due to spin of electrons will cancel out. And most of the time when the electron is moving in orbit, orbital momentum due to orbital motion is also cancelled out. If you go through your inorganic questions, right, in mains, JEE mains paper, in each paper there is a question regarding magnetic moment, spin magnetic moment in B block. So we are going to discuss this, the magnetic properties because of orbital motion and spin of electrons. If the electrons are paired, then spin magnetic moment will cancel out, and generally due to orbital motion, the magnetic moment in the atom will cancel out. So Pauli's exclusion principle, paired electrons will cancel their magnetic moment. Orbital moments of electrons also cancel out each other. So how this point is important to us, we'll go to discuss when we are discussing different type of magnetic properties. Like the first magnetic properties of substance is diamagnetic. We are saying that if the number of electrons are paired, the substance is diamagnetic, right? So what will happen, how it is behaving in external magnetic field? Suppose this is external magnetic field. In absence of, there is no magnetic field, then there is no magnetic moment in this crystal. There is no magnetic moment because all electrons are paired, so spin is cancelled, orbital will cancel, so there is no magnetic moment. But when we apply an external magnetic field, then what will happen, that on application of external magnetic field, their orbital motion get disturbed. Because of disturbance on orbital motion, they have magnetic movement because of disturbance in orbital motion, and these magnetic movements are aligned in presence of external field, and they will align in such a way that they will oppose this external field. So external field direction is this, then magnetic moment direction is opposite, and because of that we say that when a diamagnetic substance is placed in an external magnetic field, the diamagnetic substance will repel the magnet or external magnet, right? External field को repel करता है because of this alignment, and this alignment, this magnetic moment is developed because of disturbance in orbital motion of the electron on application of magnetic field. So these are weak magnetic properties. This repulsion is very weak. So what is important for us, we know that, we remember that if all the electrons are paired, the substance is diamagnetic. Some examples are given in NCERT like benzene, NaCl, water. When we study molecular orbital theory, we studied H2 molecule, Li2 in gaseous state, and fluorine molecule in gaseous state are diamagnetic. So these are examples of diamagnetic substances. Now the second point is paramagnetism. So in case of paramagnetic, we are saying that if the substance has unpaired electrons, so they have unpaired electrons, they have magnetic moments in absence of external magnetic field. If there is unpaired electrons, then due to spin of electron there is magnetic movement, but these magnetic movements in absence of magnetic field are randomly arranged. So there is no magnetism because they are randomly arranged, their net value will be 0. So in absence of external magnetic field, there is no net magnetism because random arrangement of magnetic dipoles are there. So this is the second point. When magnetic field is applied, all the dipoles are aligned in the direction of magnetic field. So they are aligned in the same direction, means they will attract the external magnetic field. So in paramagnetic substance, if we apply external field, they will attract the external field, and these substances have unpaired electrons. So like in molecular orbital theory, oxygen and boron molecule are paramagnetic in nature. Like in copper 2 plus, we can write electronic configuration and we can find out 3d10 4s1. So if we remove 2 electrons from copper, it is 4s0, and 3d9 it has unpaired electron. Because of that, it is paramagnetic in nature. Same way we can discuss about these ions, they are paramagnetic in nature. Ferromagnetism. Certain substances possess magnetism in absence of external field. When we are discussing about paramagnetism, there is no magnetism in absence because of random, but here they are saying that there is magnetism in absence of, they are permanent magnet. Ferromagnetism, permanent magnet, right? So permanent magnetic moments arise due to uncancelled electron spill by virtue of these electronic structures. So here what is important, because if you see the examples, iron, cobalt, nickel, gadolinium and CrO2, these have unpaired electrons, and paramagnetic has also unpaired electrons. So how we are going to distinguish between paramagnetic and these ferromagnetic substances? There is no theoretical way. When we bring magnet in presence of magnet, how they are behaving? If they are attracting the magnet by a strong force of attraction, then we'll say they are ferromagnetic. After removing also external field, if they behave like magnet, we'll say that they are ferromagnetic substances. While in case of paramagnetic substances, their magnetic behavior will remain in presence of magnetic field. If you remove the magnetic field, again there is no magnetism in that. So by experiment only, we cannot, on the basis of theory we can say that the substances are para substances are ferro. By doing experiment only, we are categorized that what is the difference between a paramagnetic substance and a ferromagnetic. So unpaired electrons are not only the sufficient conditions, right? But it is a easy way to say that, because these substances also have a large number of unpaired electrons. So this example is very important, given in NCERT. Iron, cobalt, nickel, iron, cobalt, nickel. Gadolinium has maximum number of unpaired electrons. And CrO2. The CrO2 is oxide of transition element which has properties like metals. CrO2 has properties like metals. So FeCO(Ni), gadolinium and CrO2. मेंस में ये क्वेश्चन पूछा गया है. Be careful about this gadolinium and CrO2, that they are example of ferromagnetic substances, and due to some structure is there, because of those structures these magnetic dipoles are aligned in the same direction. It is not that easy that we can say only on the basis of atomic structure or electronic configuration, right? There is solid state structure, and because of those solid state structure and alignment of magnetic dipole on those atoms, how they are aligned, on the basis of that we are discussing ferromagnetic substances. So it's not easy to count the number of electrons and say that the substance is para or the substance is ferro, because in both unpaired electrons are there. So for us, remembering these examples are very important. Gadolinium and CrO2, iron, cobalt, nickel, gadolinium and CrO2. Anti-ferromagnetism. If coupling of electron spin result in anti-parallel alignment, then spin will cancel each other and no net magnetic moment will arise. Again here it is related to structure of solid. Like they have given an example in NCERT, already asked in JEE Mains, that which of the following substances is anti-ferromagnetic. So MnO is anti-ferromagnetic. I have tried to explain this MnO. MnO is Na type of structure. So in Na type I have taken one phase, because we know that in case of rock salt type of structure, anion, it is FCC with respect to anion, and cation is present in octahedral void. So I have shown one phase here. Same phase, 6 phases will be there. So if one phase I am able to explain that why it is diamagnetic, we can say that oxide ion, all electrons are paired. So oxide ion is diamagnetic. But for Mn2 plus ion, if we write electronic configuration for manganese, we can find out 3d5 4s2. If we remove 2 electrons, then it is 3d5. It has 5 unpaired electrons in 3d. Because of that, magnetic moment is there. So this is because of one Mn2 plus ion, right? And in this whole structure, these 4 Mn2 plus ions are cancelling each other. Their magnetic moment alignment is equal and opposite, and they will cancel. Like we can say that these two will cancel and these two will cancel. So overall, this whole thing will cancel. For the whole crystal, all have the same type of arrangement in each and every plane, 6 faces. So the net magnetic moment is going to cancel out, right? So from experiment only we are able to find out that this is anti-ferromagnetic substance. So example is important, that is MnO. MnO is the example. I have tried to explain logically so that you can remember about MnO. Ferrimagnetic substances, they are weakly attracted in magnetic field. So what happens that ferrimagnetic substances, they have given some example in NCERT like Fe3O4, Mg Fe2O4, Zn Fe2O4. So they are ferrites, and we know about Fe3O4. Fe3O4 is not a compound, it is a mixture of FeO and Fe2O3. So here there are 4 oxygen atoms. With respect to crystalline solid, it is FCC with respect to anion, and there are 2 types of cation, iron plus 2 and iron plus 3. Iron plus 2, because it is FCC, there are 2 types of void, tetrahedral and octahedral void. All the iron plus 2 is present in octahedral void, and there are 2 iron plus 3 ions. Iron plus 3 are equally divided between tetrahedral void and octahedral void. So overall, the net magnetic moment will be there. Few are cancelled, but you can see here that this is cancelled, this is cancelled, but because of this there is magnetic moment, because of this there is magnetic moment. So they have equal and opposite. If they have equal and opposite, then it is antiferro, but it is not equal because of that. So here we are trying to explain this structure, that oxide ion is paired electrons, so there is no magnetic moment, but Fe2 plus and Fe3 plus both have unpaired electrons. So we are discussing that Fe3 plus is present, one unit cell contains one Fe plus 3, right? So their position is in octa and tetrahedral, what equally distributed in octahedral, one Fe3 plus in octahedral, one Fe3 plus in tetrahedral, and they are aligned such that they will cancel, the net magnetic moment will complete cancel because of Fe3 plus ion. But this Fe2 plus ion is present only in octahedral void, and because of this alignment, this whole substance has magnetic moment, but this magnetic moment is not very strong, so they will weakly attracted by the magnetic field. So the example is important. This is given in NCERT, Fe3O4 Mg. In place of iron plus 2 ion, we can put magnesium 2 plus ion or Zn 2 plus ion. Rest is same. Fe2O3 is same in all this, right? So in place of FeO, we can write ZnO, MgO. So these are the mixture of these compounds, and they are their crystalline structure. With the help of crystalline structure, we are trying to understand that how the ferrimagnetism is going to work. Electrical properties. In electrical properties in physics, you already study about N type of semiconductor. If silicon or germanium is doped with phosphorus and arsenic, because silicon and germanium has 4 electrons in the outermost and they have 5 electron, one extra electron is there. If we apply potential difference, this electron will move, and because of that there is N type of semiconduction. Then in ionic crystals, we have discussed that metal excess defect. Because of metal excess defect, there is N type of semiconduction, right? In case of NaCl, there are F centers. More the F centers, more will be the intensity of color, more will be the N type of semiconduction. So metal excess defect, there are two type of metal excess defect in NaCl and ZnO. They both will act like N type of semiconductor. Then P type of semiconductor, silicon and germanium doped with boron, aluminium and gallium. You already know, because in boron, aluminium, gallium, 3 electrons are there. So when there is formation of bond between silicon and boron, there is a vacant space that is known as hole, and the electron will move from some other silicon bond to that place. So that method is known as jumping of electrons, Hooke's method. So because of Hooke's method, if conductivity is there, that is known as P type of semiconduction. So this P type of semiconduction is in Fe.96O, metal deficiency defect, right? Or it is in SrCl2, NaCl2 doped with SrCl2, NaCl2 doped with SrCl2. These type of vacancy is there. Now typical compounds group, compounds of 13 and 15, because the difference of number of electrons in 13, there are 3 electrons in valence shell, while in case of 15 there are 5. So the difference in the number of electrons will be more. In 12 and 16, the difference is further more, 2 and 4 electron difference is there. So these type of substances can act like advanced semiconductor. They have a better response. So these type of questions are also important in board exam, but you should know that these compounds are acting like advanced semiconductors. 13, 15 and 12, 16, typical compound group, advanced semiconductor having very fast response. And these points are asked in and that is given in NCERT, transition metal oxide which behaves like metal. So there are 3 metal oxides they have given, TiO, CrO2 and ReO3, and we know that CrO2 is also ferromagnetic substance, because gadolinium and CrO2, it is also ferromagnetic. TiO, CrO2 and ReO3, especially this ReO3, it is looking like copper metal in appearance and properties also. Conductivity and appearance is same as that of copper. So this is a fixed method that question, that in transition metal oxide, which oxide has appearance and conductivity as that of metal, copper metal, that is ReO3. And the last point is, these are some transition metal oxide, depending upon temperature, they can have insulating properties or they can have metallic. So they are metal oxide. Usually metal oxides are ionic compound, but they have a behavior of metallic, their conductivity, their property, but those property depends on temperature. Depending upon temperature, they can behave like metal, they can behave like insulator. See, when you are giving an exam and you are searching the questions what they have asked, I'm teaching on the basis of what has been asked in JEE mains, right? So I'm not thinking that this is very logical or this is very interesting that the student will listen or not. Keeping that in mind, that what is useful to you. So whenever I'm saying that this is important, remember it. Please remember those things, right? And if you're liking these videos, right, please subscribe and like and share between your friends. Thank you.